In this video, we're going to work our way through some related rate problems here. And anytime you're looking at a question in context and you start seeing the words increasing, decreasing, growing, or shrinking, you got to remember you're talking about a rate of change. And mathematically, or using our calculus notations, the way we would represent that rate of change would be we'd take this quantity and we would be taking the derivative of that quantity with respect to time. Now, there are two key parts to solving related rate problems. The first is to remember you're always taking the derivative of something with respect to time. And when I'm doing that, I'm going to have to apply the chain rule correctly. And another way to think of it is you're using the implicit differentiation technique. The second thing that you have to do is you got to be very careful for when you're putting values in. I need to know when can I put a number in, and when can I put it in at the beginning, or when do I have to wait? And the way you can tell is rate values can only be plugged in after you take the derivative. So all rates you have to wait. The other values that are not rates, we need to decide if that value changes throughout the scenario we're looking at. If this value remains constant at all times, we can plug it in right at the beginning. But if its value depends on a certain time or an instant, then we have to wait until after we're taking the derivative. And I have some guidelines here that we can follow. It's often helpful to take a picture or draw a picture. And it's a 100% necessity to take everything that we're given in the problem, and we need to label it correctly and state what it is we're actually looking to find. After we do that, we're going to write an equation based on what we are given in context, and then we're going to start taking the derivative and plugging stuff in. Now, we got to remember, at the very end, we need to answer our question using the appropriate units, and it's oftentimes very helpful to write our answer using a complete sentence. So, let's look at our first related rate question here. And we're looking at a balloon that's being inflated at a rate of 5 inches cubed per minute. And then when the radius of the balloon is 4 inches, how fast is the surface area of the balloon changing? Well, the first value we're given is 5 inches cubed per minute. That is a rate. So I need to label that. Now, inches cubed, that's third dimension, that's volume. So we can label this as dV over dt is equal to, now if we're inflating the balloon, the volume is getting larger, so this rate is going to be positive, so positive 5 inches cubed per minute. Now we're going to look at what it is we want to find. We want to find how fast is the surface area of the balloon changing. So our end game here is we want to find the rate of change of the surface area. So I'm just going to say, I'm going to go dA over dt. A is going to represent my surface area. When the radius is 4 inches, so I'm going to go documentation line. So when r is equal to 4, that's what we want to know. Okay, well, we need to write an equation. They're talking about the volume of a sphere. So let's start with the volume of a sphere formula, which the volume of a sphere is 4/3 pi r cubed. Now, surface area of a sphere, because we're talking about a balloon, the surface area equation would be A is equal to 4 pi r squared. Now, we're given a rate. We're given the rate of change of our volume. So we do need to go ahead and take the derivative of our volume formula with respect to time. So dV over dt is going to equal 4 pi r squared dr over dt. Okay? Now, I could go ahead and put 5 in because I know 5 is dV over dt. Now that I've taken the derivative. So 5 is equal to 4 pi r squared dr over dt. Well, we're kind of going to pause for a minute. We look over and let's say, all right, well, let's take the derivative of our surface area formula because we want to know the rate of change of the surface area. So I'd take that derivative, dA over dt would equal 8 pi r dr over dt. Well, we know we're given an instant when r is equal to 4, so my problem here is I need to replace dr over dt with a quantity. Well, we have this expression over here based on our volume. We could rewrite that as dr over dt equals, and then we'd be able to substitute in and then get our rate of change of area. So if we do that, so dr over dt would equal 5 divided by 4 pi r squared. Now we're going to take that, we're going to plug that in. So dA over dt is going to equal, we would have 8 pi r times 5 over 4 pi r squared. Now we could simplify that, make life a little easier, and that's going to wind up simplifying to 10 over r is dA over dt. Well, now we'll go back to what it is we were trying to find, the rate of change of our surface area when r is equal to 4. So we're going to put 4 in for that r, and then we'd simplify, and that gives us 5 over 2. Now we have to attach units here. The rate of change of surface area, that is, area is two-dimensional, and our units are inches, so it'd be inches squared per unit of time, and our time here is in minutes. All right, new problem here. The length of a rectangle is decreasing by 2 inches per second. All right, well, I'm immediately going to stop once I start reading that, and I'm going to say, all right, the rate of change of my length of my rectangle with respect to time, since it's decreasing, it's going to be negative 2 inches per second. And the rate of change in the width is increasing at the same time by 3 inches per second. So the rate of change of my width with respect to time, it's increasing, so positive 3 inches per second. And then we continue reading on. When is the length, or when the length is 10 inches and the width is 6, how fast is the area changing? So basically we're trying to find the rate of change of area with respect to time of this rectangle when the width is 6 and the length is 10. So when W is equal to 6 and L is equal to 10. So that's what that notation means. Now, I need to make an equation now that I have everything labeled and what it is I'm trying to find. Well, we're talking about the area of a rectangle here. So the area of a rectangle is equal to length times width. We have no values that remain constant the whole time, so we immediately need to take our derivative. So the derivative of my area with respect to time is going to equal, I got to do product rule here, so first times the derivative of the second plus second times the derivative of the first, and then now we're looking and we're ready to plug everything in because we know what W over dt is, which is 3. And we know what dl over dt is, which is negative 2. And so we can go find the rate of change of our area when we put in 6 and 10. So when we put in 6 and 10, we'd have 10 times 3 plus 6 times negative 2. And we evaluate that and we get positive 18. Now I have to attach my units. We're talking about area. Area is second dimension. So my units, which are inches here, need to be squared per unit of time, and our unit of time here is in seconds. All right, this problem, a camera is placed 3,000 feet from a rocket launching pad. Rocket's rising vertically at 880 feet per second. There's a rate there. And then when it is 4,000 feet in the air, how fast must the elevation angle change at the instant to keep the rocket in sight? All right, so for this one, I'm actually going to draw a picture. All right, so we have the camera, which is going to be right here at X, and then we have the rocket launching pad. Now, a rocket is launching vertically, and it's rising here, so I'm going to put an arrow to indicate its direction. Now, the camera, its distance from the initial launch pad is 3,000. That is going to remain constant there. It doesn't change. I'm just going to make a note that that's always going to be 3,000. So the rocket is rising vertically at 880 feet per second. So I'm going to let the vertical component be y, so that way I could say that dy over dt is going to equal 880 feet per second. Now, we're looking at what it is we're trying to find. We're trying to find the change in the elevation angle. So So I'm going to close this off and form a triangle. This will be a right triangle. And the elevation angle here is going to be indicated, and I'm going to use theta. So what we're looking for is we're trying to find the rate of change of our angle, so d theta over dt, when the rocket is 4,000 feet in the air, so when y is equal to 4,000. Okay. Well, I need to start relating my sides together and my angle. So I have angle, opposite side, adjacent side. We're going to use tangent. So I'm going to say tangent of theta is equal to opposite over adjacent. Well, my opposite side is y, my adjacent side is 3,000. I need to turn that into a rate, so I need to take the derivative. So I take the derivative of my expression with respect to time. The derivative of tangent is secant squared, so I get secant squared theta times d theta over dt equals, and then the derivative of y over 3,000 would be 1 over 3,000 times dy over dt. Now, we want to write this equation as d theta over dt equals, so I'm going to move the secant squared to the other side. When I do that, and I can kind of simplify this, so instead of dividing by secant squared, I can just multiply both sides by cosine squared, and I have 1 over 3,000 times cosine squared theta times dy over dt. And we look at what it is we have and what it is we don't have. We know that dy over dt is 880 feet per second. The question is, what is cosine of theta so I can square it? Well, now we would go back to our right triangle that we made and say, okay, well, at the instant when we are 4,000 feet in the air, I want to know what that angle would be, the elevation angle. Well, I could do right triangle trig. I need to know the adjacent side and the hypotenuse side to get cosine's value. Well, we have a one leg of 3,000, one leg of 4,000, so the hypotenuse here at 345 would be 5,000. So cosine of theta would be adjacent over opposite, which would make a ratio of 3/5. So I could put that in for cosine when I'm up over here in my find line. So the rate of change of my elevation angle is going to equal 1 over 3,000 times cosine of theta being squared times 880 feet per second. And then we would simplify that, and that is going to simplify down to, well, it actually is going to make a decimal. So we're going to wind up with 0.1056, and our units are going to be radians per second. All right, new problem here. A street light is mounted at the top of a 15-foot pole. A 6-foot tall man walks away from the pole at a rate of 5 feet per second. How fast is the length of his shadow changing when he's 40 feet from the pole? All right, this is going to be one that is definitely going to make life easier if we draw a picture representing what's happening. So I'm going to draw the ground, and then I'm going to draw a vertical line that represents the length of the represents the street light. Well, the street light is 15 feet. That does not change. The street light does not get shorter at all, so that's constant. Make a note of that. All right, then somewhere over here to the left-hand side, I'm going to draw a vertical line that represents the height of the man. So the man here is 6 feet tall, and that's also constant. Doesn't change. Now, he's walking away from the pole at a rate of 5 feet per second. So I'm going to let the distance between the man and the pole here be x. And so he's walking away, so the rate of change of x with respect to time is going to be equal to positive 5, because he's walking away at 5 feet per second, so 5 feet per second. Now we want to represent where his shadow is. Well, the shadow is going to be formed by the first ray of light that will go past the man into the ground, right? And then we would make, and I can't quite draw it all the way, it's a little bit too tall, all right, but our shadow would be right around in here. So what we would do is, let me change colors and we'll indicate the shadow. So my shadow length is going to be S. We want to find how fast the length of the shadow is changing. So we want to find ds over dt when x is equal to 40, when he's 40 feet away from the pole. All right, well, I need to somehow relate my variables and these numbers together. What you have is similar right triangles. I have a smaller triangle over here that's a right triangle on the left-hand side, where I have one side of S, one side of 6. So I'm going to make a ratio here where I have 6 over S equals, and then you have the overall outside triangle where you have a vertical leg of 15, overall bottom leg of S plus X. So I have 15 over S plus X. Now, I would cross multiply and try to make things easier. So we'd have 6S plus 6X is equal to 15 times S. And we try to simplify that problem as much as we can before we worry about taking any kind of derivatives, and we'd wind up with 2x is equal to 3 times S. All right, now this is the formula that we have that relates S and X together. We need to convert that into a rate formula, so I need to take the derivative of both sides with respect to time. I do that, I take the derivative, we'd have 2 times dx over dt is equal to 3 times ds over dt. Now that we can see everything that we have, our end game here is to find ds over dt, so I divide by 3. And so 2/3 times dx over dt is equal to the rate of change of my shadow length with respect to time. So now we can plug in our stuff. So the rate of change of the shadow with respect to time would be equal to 2/3 times the rate of change of the distance of the man from the pole, which was positive 5. And we just multiply those together and we get 10 over 3. Now I need to attach my units. Well, S is feet. So ds over dt be equaling 10/3 would be feet per unit of time, so feet per second. All right, last problem here. A rainbow snow cone is leaking from its paper cone at a rate of 2 cubic inches per minute. The paper cone's top radius is going to be 3 inches, and the height is 5 inches tall. I want to know how fast is the radius of the cone changing when the radius of the snow cone is 2 inches at that instant. Okay, so what I have is I have a diagram of my paper cone in black. So the paper cone does not change because that is what the actual snow cone is inside of. So it has a radius of 3 inches and it has a fixed height of 5 inches. Now inside of this paper cone is going to be what's left of the snow cone that is leaking. So inside of it, my snow cone, I have a radius of R and a height of H in blue. Now, we have that diagram. We need to go in and we need to label what it is we're looking at, or what we have in context of this problem. So the snow cone is leaking out of the cup at a rate of 2 cubic inches per minute. Well, cubic inches, that's third dimension, so that's the rate of change of volume. So dV over dt is equal to, we're leaking out, so it'd be negative 2 cubic inches per minute. And they want me to find, so our goal is to find how fast the radius of the cone is changing, so that would be dr over dt, when r is equal to 2. Okay, well, let me zoom in here on this picture. I need to relate my values and r and h together. Well, we have inside of this cone similar right triangles. We have the ratio of the radius to the height of the snow cone, and that's going to equal the ratio of the radius of the paper cone to the height of the paper cone. And what I would do is I would cross multiply here, and so that way we're not necessarily working with a fraction. We'll figure out how we're going to proceed after this stage. So I have 5r is equal to 3 times h. Now we'll go over to our negative 2 inches cubed per minute. This is a unit of the rate of change of volume. So I need to write a formula for the volume of a cone and then take its derivative. The volume of a cone is equal to 1/3 pi r squared h. And before I take the derivative, we need to look at what the information is that we have. We know that r is equaling to 2 somewhere. We also want to know what dr over dt is. Notice how there's no reference to the rate of change of the height. So what we're going to do is we're going to use this ratio equation that we came up with, and we're going to rewrite as h equals, so that way our formula doesn't have an h in it, it only has r's. So I'm going to turn around and I'm going to divide by 3, and so we have 5/3 r is equal to h. And we're going to substitute that and rewrite our volume formula. So our volume formula would be 1/3 pi r squared times 5/3 r. And we may as well simplify that as much as we can before we start taking the derivative of it. And we simplify it, and it winds up making 5/9 times pi times r to the third. Now we can take the derivative. So the derivative of everything with respect to t would equal, we would have 5/3 pi r squared dr over dt. So we have a derivative line. Now we go back and we look at what it is we're trying to find. We want to find dr over dt. So we're going to rearrange that formula to be dr over dt equals. So dr over dt would equal dv over dt times 3 over 5 times pi r squared. Now we can plug in our units. Well, now we come to our find line. Now that we know what dr over dt would be, dv over dt is -2. So I have -2 times, we have 3 over 5 times pi times 2 squared. And then we would just simplify as much as we could from there. And we're going to wind up getting -3 over 10 pi. And we have to attach our units. Well, we're looking at the rate of change of our radius. Well, we measure the radius by its length. Our length units here are going to be inches per unit of time, and our time is measured in minutes.